Can you see my screen?
Yeah. Are you ready to speak now?
I am.
Okay. Yeah. So next speaker is Patricia Klein from University of Minnesota. She'll be telling us about Bumpless pipe dreams. Yeah, please.
Thank you so much for having me. I'm my first FibSac, and I'm so glad to be able to be here, even if virtually. Thank you to the organizers for to organize a hybrid conference. So I'm talking today about Bumpless pipe dreams and Schubert polynomials. This is all joint work with Anna Weigandt, who's currently at MIT, but about to enter the tenure track market. So I'll go ahead and start with a little bit of geometry, but the geometry is all going towards counting finitely many points of intersection. So there will be non-negative integers that are at the center of this story. So what's the complete flag variety? A flag is a chain of vector spaces where we increase the dimension of the vector space by 1 with each containment. So one way to construct a flag is to take your favorite invertible n by n matrix and take the span of the first column, span of the first 2 columns, span of the first 3 columns, and so on. It is not the case that 2 different invertible matrices necessarily give us 2 different flags. A cheap example is if we take the identity matrix, or if we take 2s along the main diagonal, this will give us the same flag. And so if we want to think about the general linear group and the space of flags, then one way to give us a construction that records exactly the information that we want is to notice that the general linear group acts transitively on the space of flags. And so we can use the orbit stabilizer theorem, really, to construct the space of complete flags from the general linear group. So the upper triangular matrices, these stabilize the flag that's determined by the identity matrix. And so we can identify the space of complete flags with GLN mod this stabilizer. So through this identification, we can inherit some topology. And the way we're going to do that is by recalling in linear algebra class that we took our invertible matrices and we had these LU decompositions where we could write most invertible matrices as a lower triangular matrix times an upper triangular matrix. And occasionally we had something like 0, 1, 1, 0, where we couldn't do that and we had to change the order of the rows. So that's what this permutation matrix there, W, is doing. So it turns out that there's a unique choice of permutation that we can put there. And in particular, GLN breaks down as this disjoint union that's of these, L times a permutation times U. And so the permutation matrices index these cells. So this is called the Bruja decomposition of GLN. We have a surjection from GLN to the space of flags. And so we can just push down each of these cells in our disjoint union to the space of complete flags. And then we'll want to take a closure and we get what are called Schubert varieties. Okay, so we might want to intersect our Schubert varieties and think about how they intersect and count some points of intersection. And it turns out that the cohomology ring, so the information about these intersections, is actually just a polynomial ring over the integers in n variables modded out by the ideal generated by the non-constant elementary symmetric polynomials. So this decomposition indexed by permutations gives rise to some intersection theory that we'd like to do. And this intersection theory has a lot to do with these non-constant elementary symmetric polynomials. it turns out that this quotient is a particularly well-behaved quotient. We can choose these nice representatives called Schubert polynomials given to us by Lescu and Knutson. And often when we multiply in a quotient ring, we multiply our representatives, we have to do a lot of cleanup, and we have to worry about when something is zero and when something's non-zero, and add some things in from the ideal we're quotienting by, and then we can re-express things in terms of our chosen representatives. And one thing that we really like about Schubert polynomials is that we don't have to do this cleanup. If we multiply two Schubert polynomials, then we get a sum of other Schubert polynomials on the nose. This is not up to an element of I. So when we want to do our multiplication in this quotient ring, we can, kind of do what we've wanted to do since Algebra 1 and almost pretend that our quotient ring is a subring. And that's not really true, but we mostly don't have to think about, cosets and quotienting. So this is clean. And it turns out that these coefficients that show up in our expansion when we multiply our two representatives in this cohomology ring, these are called the Schubert structure constants. They are non-negative integers, and what they do is they count points of intersection of Schubert varieties determined by U, V, and W. So it's counting points of intersection in varieties that tell us about multiplication in this cohomology ring. So this is one reason why we really like Schubert polynomials. We really like the Schubert structure constants. There's also an equivariant cohomology story that behaves fairly similarly. And we're actually going to be studying today these double Schubert polynomials. So the Schubert polynomials that we'll be thinking about come from some more complicated cohomology, and the meat of the story is that there is a cohomology theory that is well tracked by these particular polynomials that have a lot of combinatorial content. And maybe the last thing I'll really say about the geometry is that recall again that we can take the general linear group and surject onto the complete flags. Of course, we can take invertible matrices and inject into the space of all matrices. And so in this way, we can go from Schubert varieties in the complete flag variety, pull back to the general linear group, go from the general linear group to matrix space, and arrive at an affine variety. So when we close up there, then we get an affine variety. And it will be studying this affine variety that will tell us a lot about how to write down these Schubert polynomials explicitly. Okay, so from this decomposition of the general linear group indexed by permutations, we have now gotten ourselves to an affine variety. These affine varieties are indexed by permutations. And so here I want to tell you really concretely how to start from a permutation and get an ideal in a polynomial ring. So our permutations, we'll think of them as permutation matrices. And so for example, 2, 1, 4, 3, conveniently an involution. So if your convention is the opposite of mine, we'll both be happy today. So this 2 is telling me to put a dot here in the second column. This 1 is telling me to put a dot in position 1 here. This 4 is telling me to put a dot at 1, 2, 3, 4. This 3 is telling me to put a dot at 1, 2, 3. So this is just our one line notation going to a permutation matrix. And our rule for getting generators out of this is called a rota diagram, is from these dots that we've put down, we're going to shoot out what are commonly called death rays. down and to the right. So down and to the right, down and to the right, down and to the right. And now we have some blank boxes left over. And we're going to put rank conditions into those blank boxes. So what we do is we stand on our blank boxes and we look north and west and we count the number of dots that we see. So on this box looking northwest, we count 0 dots, and so we put a 0 there. I'm standing on this blank box, we look north and we look west and we count 1, 2 dots. So we put a 2 there. And what these numbers are telling us is in a generic matrix, what rank are we allowed to have? So we fill just a matrix full of unrelated variables like this. And then we say, okay, in this northwest corner, I am only allowed to be rank 0. Well, how do I force a matrix to be rank 0? I have to insist that all of the 1 by 1 minors vanish. So I just have one 1 by 1 minor in this 1 by 1 square, and that is Z11. So I have to force Z11 to vanish. So I'm going to throw it into the ideal that I'm going to quotient by. Similarly here, this 2 is telling me that in the northwest 3 by 3 corner of my generic matrix, I have to be rank at most 2. And how do I force a matrix to be rank at most 2? Well, it's 3 by 3 minors have to vanish. In this case, it's determinant. And that's how I'm getting this generator here. It's all of the 3 by 3 minors northwest of this box there. So here's a larger permutation with a more complicated rota diagram. And so just again, this 0 is saying we have to be rank 0 northwest of that square. So that's telling me to put into my ideal these 3 variables. So Z11, Z21, Z31. This 0 is telling me to be rank 0 in that location. This 1 is telling me to be rank at most 1 in this submatrix. So all of these 2 by 2 minors are going to vanish, and so on. So it's enough to say, because all of our rules say northwest of, it's enough to take these boxes that are in gray. These are called the essential boxes, because if I'm rank at most 2 northwest of there, then I'm certainly also rank at most 2 in the smaller region. So this box is not essential. Later we'll be talking about, in particular, these 3 locations here, which we'll call lower outside corners. So we're going to be doing manipulations at these locations where there are only wires going on below it. So there's the last place where there's any information, the last place where there's anything exciting going on. So here, here, and here. Okay, so here's the formal definition of matrix Schubert varieties, which if you've seen it before and want a reminder, here it is. If you haven't seen it before, I would recommend, I guess, thinking about the example more than about this definition. And the theorem due to Fulton has, maybe most importantly for us, this combinatorial information here, that the height of the ideal is the same as the Coxeter length of the permutation, which is the same as the number of blank boxes, whether essential or not, in the rota diagram. So when we cancel a box, we're going to be decreasing the Coxeter length of our permutation, so decreasing the complexity of the situation. Some good algebraic information is that these ideals are actually prime. We're defining irreducible varieties. And that all matrix Schubert varieties are Cohen-Macaulay, which is, for commutative algebra, it's just a way of saying good. These are really good varieties that are amenable to study in a lot of the usual commutative algebraic ways. So we like them. Okay, so I've promised you that matrix Schubert varieties should help us write down Schubert polynomials, which we like because the Schubert polynomials record information about the cohomology ring. So pipe dreams were introduced by Bergeron and Billy, and then a few years later studied similarly by Flamini and Kirillov. They weren't named until Knutson and Miller, but these objects were in the literature before they were named. So these squiggles correspond to 2143. And their reduced pipe dream is just defined as a certain tiling of the grid, and it corresponds to a certain permutation. And so these are the 3 pipe dreams for the permutation 2143. And I've told you that they can help us write down Schubert polynomials. So the rule for getting the Schubert polynomial, the double Schubert polynomial, from the pipe dreams is that we look at the crossing tiles. So we have a crossing tile at 1, 1, which is giving us that 1, 1. We have a crossing tile at 3, 1, which is giving us this 3, 1. And we have in this one, crossing tile at 1, 1, giving us 1, 1. Crossing tile at 2, 2, giving us 2, 2. And then the same for the third pipe dream. This relationship between the pipe dreams and the Schubert polynomial was shown by Knutson and Miller to have another arm. And this other arm is that it relates to the geometry of the matrix Schubert variety. So there are these particularly good generating sets for ideals. They're called Gröbner bases. And a good thing about Gröbner bases is that if you take we're going to put an ordering on the monomials, and then we're going to take the largest term of every monomial in our Gröbner basis, and that will generate an ideal that's very similar to the ideal that we started with. So it's called the initial ideal with respect to that term order, and some good information is that that monomial ideal shares a Hilbert function with the ideal that we started with. So any size information that's carried by the Hilbert function is preserved. So if I say Gröbner basis, and this isn't a thing that you like to think about, then it just means a good generating set where the monomial ideal that we get out of it tells us things that we care about. So with respect to a term order, where the biggest term in our determinant is always the product of terms along the anti-diagonal, we get that, this 1, 1, which was this 1, 1, is also this 1, 1 showing up as a component of the initial ideal. And this 3, 1, which is this 3, 1, is this 3, 1. I think it's also that 3, 1. So showing up as a prime component of this anti-diagonal initial ideal. So we have a relationship between pipe dreams and the Schubert polynomial, and this monomial ideal that's associated to the defining ideal of the matrix Schubert variety. There are these other combinatorial objects that came about more recently. They were named by Lamley and Shimozono as Bumpless pipe dreams, and they appeared under the name of the 6-vertex model, coming from statistical mechanics in Lascaux's work, and then formalized in Weigandt's work more recently. And it turns out that these combinatorial objects also can help us write down the Schubert polynomial in a sort of complementary way, where we look at blank tiles. So this blank tile is in position 1, 1, which is that 1, 1. This blank tile is in position 3, 3, which is that 3, 3. 1, 1, 1, 1, 2, 1, 2, 1, and so on. So we have these other combinatorial objects, and they also tell us how to write down the double Schubert polynomial. We're going to be talking a little bit more about Bumpless pipe dreams than we did about pipe dreams, so I want to say a little bit more about what they are. So this one here is called the rota Bumpless pipe dream. So this is like the rota diagram that we've been writing down for a few minutes now, except we make the dots a little bit curvier. And there's a rule where there are modifications that we're allowed to do. So these are called droop moves. And the way that we do a droop move is we look inside of a rectangle where we have a downward facing elbow in one corner and a blank tile in the other corner. And we droop the pipe from that downward facing elbow into the blank tile. So here it is drooped in that way. Our other option is to take the downward facing elbow here and droop it into this blank tile there. So when we do that droop move, we get that this bumpless pipe dream over here. So one would naturally define these bumpless pipe dreams just as a tiling of a grid subject to certain rules. And then it's a theorem due to Lamley and Shimozono that you can get all of the bumpless pipe dreams for a certain permutation by starting from its roto bumpless pipe dream and performing droop moves. Okay, so I'm saying this is a coincidence in need of explanation. What I mean by that is that here is the formula for the double Schubert polynomial that we get from the bumpless pipe dreams. Down below is the formula for the double Schubert polynomial that we got from pipe dreams. And if we FOIL and recollect terms, we can see that these are the same polynomial, but they're not the same polynomial in any sort of obvious way where we map, term by term. So it's not the case that this x3 minus y3 appears as any of these terms. So it's the same polynomial, but not in an obvious way. And so we saw that the pipe dream formula came with some geometry attached to it. And so it's natural to ask if the bumpless pipe dream formula also has carries geometric information for us, or if it lives on its own. And so here's an example that suggests an answer, which is that this is a Gröbner basis. If our rule is that instead of taking the biggest term to be product of terms along the anti-diagonal, we want the biggest term of the determinant of a generic matrix to be the product of terms along the main diagonal. In that case, it turns out this is a Gröbner basis. And then what we get is 1, 1, 3, 3 gives us 1, 1, 3, 3. 1, 1, 2, 1 gives us 1, 1, 2, 1. 1, 1, 1, 2 gives us 1, 1, 1, 2, and 1, 1, 1, 2. So at least in this case, we're getting that a diagonal Gröbner basis is telling us that the Schubert polynomial is coming from the geometry of the initial ideal. And indeed, that's true. So my result with Anna is that if we proceed lexicographically from one of these lower outside corners, then every droop move is giving us a step in a Gröbner degeneration. So a step where we're starting from a Schubert determinantal ideal and moving towards a monomial ideal. So droop moves reflect steps in a Gröbner degeneration. So an example of this is the theorem is actually also true for these intersections of Schubert determinantal ideals. And I'm going to choose this example in order to showcase how multiplicity works. So here are all of the bumpless pipe dreams associated to these two permutations here. And so these bumpless pipe dreams just have one blank tile. This one's at 2, 2. That's giving us this 2, 2 in the initial ideal. This is a 1, 1, and that's a 1, 1. And that's telling us that we have two copies of the prime Z1, 1 in our degeneration. So one thing that's different about bumpless pipe dreams and pipe dreams is for bumpless pipe dreams, you can have two different bumpless pipe dreams with the same set of blank tiles. And that gives you the same prime in the initial ideal twice. And for pipe dreams, you don't have two different pipe dreams with the same set of crossing tiles, so you can't get any primes with multiplicity. So I guess I will 1 minute, just give you a quick picture of how we sort of step through things and simplify them. And that's that as we do a Drup move, we're separating into the primes that contain the variable at this location and the primes that don't. And we're getting that by either freezing this square, and we kind of freeze it by going to a permutation that is smaller by multiplying by a transposition and decreasing the Coxeter length, or by getting permutations that are the same size, same Coxeter length, but where the boxes move northwest. So we have these 3 recurrences. One of them is splitting up the primes into primes of a shorter permutation and primes of permutations of the same length, but where the boxes move northwest. Splitting our bumpless pipe dreams into places where that lower outside corner is a box or places where it's not. And we get this, what's called transition equation, where we can express the double Schubert polynomial of W in terms of the double Schubert polynomial of these permutations that show up through our Drup moves. So I am out of time, and so I will stop here.
Questions?
So I'm going to say something geometric, and hopefully I have the words right. But the main kind of thing I'm thinking of is the vexillary case. And in that case, my understanding is the Drup moves correspond to, if you look at the boxes, it's the elementary excitations, if you think of it as a excited Young diagram. And I was wondering if you have a relation with the ideal here and the localization of Schubert classes in the equivariant cohomology, the T equivariant cohomology in the work of Ikeda and Naruse, and they reference someone else in type A, and I forget who, but yeah, if you can say something about that.
Sorry, some of the audio came through a little bit crackly, but I understood enough of the words to know that I don't know the answer to your question, but that it sounds very reasonable. So I think I don't have a useful answer.
Thank you. Can I ask another question, or someone else have? So can you see the integrability of the vertex model in either the ideal or the geometry?
I don't know what that means.
All right. Well, I mean, just a quick sketch. You have, since you mentioned it, it's a 6 vertex model, it's an integrable one. So there's an existence of an R matrix that you can move through, and in some ways it's maybe better to think of it as a colored vertex model. And so this is a special property, and I've been curious about if there's a interpretation of this in the geometry. So yeah, thank you.
Another very reasonable question. I wish I knew.
Can I ask a question? Very nice talk. It was really good. One thing I've been wondering about this is, are you getting the exact same Gröbner basis, or is it a different Gröbner basis, like with a different degeneration order or something, when you use bumpless pipe dreams as opposed to Knutson and Miller way originally?
Sorry, say that one more time. The exact same what?
Are you getting the same Gröbner basis, reduced Gröbner basis, when you use the bumpless pipe dreams, or is it different than the original Knutson and Miller one?
Different. So the Knutson Miller one is only a Gröbner basis in the vexillary case by Knutson Miller Young work. And so in general, we don't know the Gröbner basis. We can find the prime components with their multiplicities, but the actual Gröbner basis can depend on the term order in the diagonal case. And so we only know Gröbner basis in what's called the CDG case after work of Conca-Denegro and Gorla. So we only in special cases know a Gröbner basis at all, and we know that it can vary depending on the term order, and we know that it's only the Knutson Miller, only the Fulton generators in the vexillary case.
Okay, thanks. That's good clarification.
Thanks for the question.
So for the pipe dreams, the shoot moves that generate the poset that were introduced by Bergeron and Billy, if you just generalize them very slightly, the poset you get has a lot of structure. In particular, it seems to be a lattice. Is there some structure that can be seen in the poset of group moves?
So the McNeil completion of Bruja order on SN gives us the lattice of ASMs, and these CYI, these intersections that we get out, these are ASMs. So the natural poset that we're seeing is just completing Bruja order and then getting, ASM for alternating sign matrix. So we're getting alternating sign matrices showing up in the decomposition here.
Oh yeah. If you have more questions, then I guess you should email her. So let's thank the speaker again.